Well, we just have 3 days of class left. As I was preparing for class today, trying to think about what would be most beneficial to do. And, my initial thoughts were, as I suggested in the reading for that I signed on Tuesday, to continue mixing theory with practice. But, it just sort of feels like with the rush of the end of the semester here that probably we need to focus a little bit more on the practice of how you apply this stuff, applied stats, and the technology. And really, I didn't have a ton of time to focus on thinking about R. So today, I think I'm still going to stick with what we're more familiar with, and that would be spreadsheets and Mathematica, and really try to tease out how to apply this stuff in real life within spreadsheets and Mathematica. And next week, we'll get to R, okay? And as far as the reading goes, I still want you to do the reading and try your best to understand the theory. I'm thinking in particular section 12.3. Let's see here. Section 12.3, properties of least squares estimators. Try your best to understand that theory. And in fact, I'll even share a video that I made a couple of years ago about this section where I go through the theory and I go through the derivations in here. But I think I'm not going to take time in our class to go through these things. We will make use of the results that you'll find in this section. We'll make use of the results in this section and the following sections of the various kinds of formulas and trying to understand those and how to use them in the context of our technology, which you pretty much have to do even if you understand the theory. In order to implement it, you pretty much have to do the technology because the calculations are just too nasty if you don't use the technology. But as far as understanding the theory, I'll leave that to you, okay? I might still assign some problems related to understanding the theory, so you should still make some effort to do it. And the problems, I don't know how difficult they might be. I'll try to make them probably more basic, but some effort should be made on your part, okay? But let's talk about applying the ideas. And let's go ahead and just jump right into spreadsheet usage with home price data. Now, I just emailed you the spreadsheet as an Excel file before class. So you could open an Excel, and certainly if you've got a PC and you've been able to do Excel Miner on your PC, you could keep it open that way. I'm also allowing you to view on Google Sheets, as I see some of you have joined, and that's great. If you haven't opened up the Google Sheets, you can do that now. It's what you might call a more realistic data set, a bigger data set. There's 500 and something data points here. 504 data points. The first column, column A, is labeled OBS, I believe, for observation number, indicating you got 504 data points. What's these data about? You can see the title is home price data. This is the prices. This is evidently pretty old data. You would hardly be able to find many houses, at least in a city and the suburbs, even close to those prices. Maybe it's a really old data, or maybe it's a very small, well, it can't be a very small town because there's 504 data points. Prices for different houses, square footage, pretty small houses by today's standards here. Maybe this is an old town in rural Minnesota, but again, there's more data points than you would typically find for homes on sale, at least. Maybe this is not just homes on sale, but also all the homes in a town. Number of bedrooms, number of bathrooms, number of garages. You can see there's many houses with 0 garages. Yeah, with old construction, old homes, many times there are no garages and people have to park on the street. And the zip evidently refers to perhaps a last number in a zip code, indicating maybe the area of town where the home is in. Big picture wise, we'd be wondering, how do these variables, square footage, number of bedrooms, number of bathrooms, number of garages, or maybe number of cars the garage can hold, because I think sometimes there's 1 or 2, if it's a 1-car garage or a 2-car garage, and maybe a 3-car garage, and the zip code, how do they affect or predict the price? So you think of these 5 variables as being explanatory variables or predictor variables, and 1 variable, the price, as being the response. These would all be x's, and x1 and x2 and x3 and x4 and x5, and this would be your y. Okay, what's the model? Let's write down the multiple regression model here. Multiple regression model. Write it first in terms of the theoretical mean. Mu of y given x, meaning for a given x value, assumed to be known, what is the mean of the corresponding y's? Remember, y is going to be the price of the home. We are going to assume this is a linear regression model. It's got a constant term, beta 0. And some linear function of the x's, beta 1 times x1, plus beta 2 times x2, plus beta 3 times x3, plus beta 4 times x4. I think there was a 5th variable. Square foot, bedrooms, bath, garage, zip. Yes, 5 explanatory variables or predictor variables. Beta 5 times x5. So this is an assumption about how the mean of y depends on the given x's. Y is going to represent the price. X1 is going to represent, let's just go in order here, square footage. X2 will be bedrooms. X3 will be bathrooms. X4 will be garage. X5 will be zip. This is square footage. That's the number of, was it bedrooms or bathrooms? I forgot. Bedrooms, yep, bedrooms. I'll just call it bed, bath, garage, and zip. Excuse me. Now you might wonder, one thing kind of weird here is certainly square footage, bedroom, number of bedrooms, number of bathrooms, and number of cars your garage can hold are quantitative variables. And the zip code, or at least the last digit in the zip code, is a number, but is that really a quantitative variable? I mean, what determines what the last number in a zip code is? It's not really a quantitative variable in the usual sense. It's more of what you might call a categorical variable, though we are using numerical label for it. So you might wonder whether this is really valid to do. Let's just go ahead and assume it's valid and see what happens. Okay. Another thing to think about is the number of bedrooms, bathrooms, and garage, cars the garage can hold. Maybe better to label that car, are relatively small numbers. Well, there are some zero car garages because some houses don't have garages, but you might have a 1-car garage, a 2-car garage, or a 3-car garage. For bed and bath, you might have 1, 2, 3, maybe 4. They're not real big numbers. Square footage can be a fairly big number, and you might say the square footage, even though it's going to be a whole number, in theory, at least when you're round, is better modeled as a continuous variable, whereas bed, bath, garage are more discrete. So again, that might cause some confusion about whether this is really valid, but let's just go ahead and assume it's okay. Then an individual observation for y, thought of as a random variable, would be the mean, which would be given by all this, plus some error term. I'll call it E sub I. I have written this kind of equation before without subscripts, but mostly you've seen in the book, mostly they write with subscripts. And here's your random part. That's where the randomness comes in. That's a random variable. All this other stuff's not a random variable. And all these E's are assumed to have the same distribution and are also assumed to be independent. I haven't emphasized this much, but I actually emphasized it a lot when I taught this class 2 years ago. These random variables are independent and identically distributed. Identically, can I spell it? Identically distributed random variables, sometimes abbreviated IIDRV or DRVs. Independent and identically distributed random variables. They are all normal with mean zero and variance sigma squared, where sigma squared is unknown and has to be estimated. We just assume there's some positive number sigma squared that represents the variance of all of these when we set up the model and derive the properties of the model. But then that kind of thing has to be estimated from the data, as usual. Does this fit under the rubric of the general linear regression model? Remember, we also saw on Tuesday that the general linear regression model could involve squares of variables. I also mentioned it could involve products of variables, which is not linear in the usual sense. This is certainly linear in the x's. But the thing that really makes it part of the general linear regression model is the fact that it's actually linear in the betas. The parameters that we'd like to estimate. That's where what allows you to set up a design matrix, model specification matrix. I like design matrix better. And write everything in terms of that design matrix. Let's go ahead and imagine doing that in this situation before we go back to the technology. What would the design matrix be here? It's called capital X. In all these situations, the first column is always a bunch of ones, which effectively corresponds to the fact that you've got a constant term, beta 0. Actually, you could set up these models without a constant term. Maybe you hypothesize that the constant term should be 0, and so you don't include it. And then you would not have a first column of ones if you set up your model differently. There would be a different background assumption, effectively. How many rows are there? There's n rows. N rows. And how many columns will there be? The number of columns corresponds to the number of betas. Now the subscripts on beta start at 0. So you can see since the last one's beta 5, that means there's 6 betas. That last subscript in general is typically labeled with the letter K in the book. And so in general, there are K+1 columns. N is the number of data points for your random sample. K is the standard letter for the subscript of the last beta and the last variable in this kind of equation, meaning there are K+1 betas, if you allow a constant term at least, as we always are going to do. N rows, K+1 columns. In this example, K is 5, so it's going to be 6 columns. 6 columns for the example. And actually, we know from looking at the data set in the spreadsheet, there were 504 data points. N is 504. (504 rows for this example. This is a large matrix. Sorry that I wrote over the arrow there. 504 rows for this example. This is a big matrix. 504 rows, 6 columns. What do the other 5 columns look like? Effectively, each data point, so to speak, goes across the rest of the rows. An X1 value, an X2 value, X3 value, X4 value, X5 value. For the first data point, that is X1 sub X sub 1, 1, meaning the first coordinate of the first data point. The next one you'd label X sub 2, 1, meaning the second coordinate of the first data point. Then X sub 3, 1 for the third coordinate of the first data point, X sub 4, 1 for the fourth coordinate of the first data point, and X sub 5, 1 for the fifth coordinate of the first data point. Then in the next row, you'd have X sub 1, 2, the first coordinate of the second data point. 2, 2, second coordinate of the second data point. 3, 2, third coordinate of the second data point. 4, 2, fourth coordinate of the second data point. And 5, 2, fifth coordinate of the second data point, etc. The last one would be your nth data point. Its first coordinate is X1n. Its second coordinate is X2n. Its third coordinate is X3n. Its fourth coordinate is X4n. And its fifth coordinate is X5n. That's your design matrix. What are the normal equations? Well, we should also write down the data. You could call this the y data vector. Y1, Y2 through Yn. What do those normal equations look like that you have to solve? If you recall from Tuesday, after taking partial derivatives, setting them equal to 0, and rearranging the equations in matrix form, they look like this in the end. X transpose times X times the unknown vector that is going to give you your parameter estimates, B, equals X transpose times Y. These are the things that are analogous to those equations with all the summations in them. By the way, I forgot to mention the book uses X prime for X transpose. It doesn't mean derivative, it means transpose. I prefer using a T. It's okay if you use a prime. And I said it can be verified if you've got at least 2 data points with distinct X values. X transpose times X will be invertible. And you can multiply both sides of this equation on the left by its inverse to solve for B. We should think about the dimensions of these things. Again, in the general case, X is n by k plus 1. It's transpose, where you flip the rows and columns. Every column of X becomes the corresponding row of X transpose. So like, since the first column of X is all ones, the first row of X transpose would be all ones. Since X is really tall and skinny, X transpose is going to be short and wide. You switch these around. This one's going to be K plus 1 by N. Those inner ends match, so you can do the multiplication. Got a match there. And the result is a square matrix that is K plus 1 by K plus 1. Think about Y. Y is an n by 1 vector. It's getting multiplied by X transpose, which, as before, is K plus 1 by N. Those match, so you can do the multiplication, and you're left with a K plus 1 by 1 column vector in the end. If this is all going to work, B has to be K plus 1 by N, right? If you're going to be able to do that multiplication there, the number of rows of B has to match K plus 1. It's got to be K plus 1 by 1. And it's got to match that. So you ultimately have a system. The normal equations are ultimately a system with K plus 1 equations. The B, the components or coordinates of the B are B0, B1 through BK. Because they're trying to estimate the betas, which are beta 0 through beta K. Right, this thing here is B0, B1 through BK. Those are going to be your estimates for the betas. For a particular data set, those are going to be numbers. In the abstract, which you're going to think about when you read section 12.3, they're going to be estimators, statistics, random variables that have distributions. And the entire vector itself even might be said to have a distribution that has a certain vector mean and a certain vector variance, although you'll see the vector mean is indeed a vector, but the vector variance is actually a matrix called the variance covariance matrix. Yikes. Although it's not quite as complicated as it looks, in this setting of general linear regression, this vector covariance, variance covariance matrix simplifies quite a bit. By the assumption of independence, all those covariances you see are zeros. And all these variances along the main diagonal are actually the same number. They're all sigma squared. So you actually get a multiple of the identity matrix. It simplifies quite a bit. If we were not doing a general linear regression model and we didn't assume independence, then we'd have to deal with the complications you saw in that matrix. But in this setting, it simplifies quite a bit. That's good. But again, I'm leaving that to you for the reading and perhaps some homework problems based on the reading. Let's now go back to the spreadsheet. Well, we should also solve this, I guess. This implies ultimately that B is X transpose X inverse times X transpose Y. Is that big enough to see? And again, X transpose times X will be invertible as long as you've got at least two distinct data points with distinct X values. At least one of the X values is different than the corresponding one for the other one. Realize what's going on here, though, to compute this. X transpose times X could in general be a pretty big matrix. I mean, for our example, even though we've got 504 data points, it's not super huge. K plus 1 is 6. It'd be 6 by 6. Well, that's big enough. You wouldn't want to do that by hand for sure. Computer can certainly handle it, inverting a 6 by 6. But, you know, what if you had hundreds of variables? Are there ever situations where you do have hundreds of variables? Actually, yeah. If you took operations research, there are many industrial situations where you've got hundreds of variables. And you could have like 100 by 100 matrix or 1,000 by 1,000 matrix. And technically speaking, to invert such a matrix is hard even for a computer. So what do? There are ways around actually inverting the matrix. You actually go back to the normal equations and you try to do other methods that are quicker. It's a subject for numerical linear algebra. You'll see hints about what's done in your linear algebra book. I think if you look at the end of chapter, well, if you look in the section, I think it's in chapter 6 about least squares in your linear algebra book. They talk about some numerical issues about how to solve such systems more quickly. Okay, it is an issue, but we're assuming the really advanced people who thought about such issue have taken care of it. Evidently they have, because we've got the technology that can do it even in just a spreadsheet, you might say. So let's go ahead and do it here. You can watch me on your computer if you like here. So again, 504 data points. The last data point is in row 505. We got the labels in row 1. We're after trying to do inference here. We're trying to look at doing hypothesis testing and confidence intervals for these parameters, beta 0, beta 1 through beta 5. That's the most fundamental thing to be able to do. And then the spreadsheet can't do this, but Mathematica and R can. We're also after confidence intervals and prediction intervals to estimate means, the mean of y and y values when you know x. Like, how much is my house going to be worth, for example, if I know my square footage, if I know my number of bedrooms, etc. What would I predict for what I could do for the sale price? That's the application in this context. Click the labels box. Can you, when you're viewing it, so I shared it with you for a view, can you see what I'm doing live? Okay. Click the labels box. Y range, that's the price, that's column B. B1 colon B 505, 504 data points. X range includes all the other columns, C through G. So I want C1 colon G 505. That'll highlight, pick all those columns together as all the X's. Again, there's 5 explanatory or predictor variables. Okay, does that make sense? Keep track of what you're trying to predict. It's the price we're trying to predict, not something else. So that column B has got to be the Y. And the other columns that come after it have to be the X's. I mean, could you try to predict, say, the number of bedrooms if you knew everything else? Yeah, but it kind of doesn't make as much sense. Makes more sense to say we're trying to predict the price. Well, let's put the output starting I1 for the upper left corner. And let's just click OK. Did I click it? Or is it just working? There we go. Okay. Took a few seconds. Let's think about the output here. I do want to start to get into interpreting the Anova part of the output today as well. Let's go down to the easiest part to interpret, the bottom. These are our parameter estimates. You'd label this B0, this one B1, this one B2, this one B3, this one B4, this one B5. Fortunate that the variables have the actual labels up here, so you can see those labels down there, and you don't have to always remember, oh yeah, X2 represents the number of bedrooms. You can see it there. These are estimates, point estimates for the unknown parameters, beta 0 through beta 5. But they are observed values of theoretical statistics. And remember, one of the most importance of all inferential statistics, if we had a different sample, we'd get different estimates, right? That's a really important point to realize. If you had a different sample of different houses in the same town, say, you'd get different parameter estimates. The estimators, B0 through B5, are in the abstract statistics that are random variables, that have distributions, that have sampling distributions, that typically look like normal curves. And in fact, they are normal curves in the model. They have normal distributions. To do tests on them, though, to do both hypothesis testing and confidence intervals, we do have to use an estimator for sigma squared, right? S squared. And because of that, we end up using a t distribution in the end with a certain number of degrees of freedom. That still happens here. They have standard errors. These things are estimates of standard deviations of sampling distributions. I've said that before. I like labeling them based on the way the stat analysis book that I use labels them. Our textbook does not do this. SE for standard error of, say, B sub I. That's called the standard error of BI. Actually, I probably should use a capital B. Capital BI as an abstract estimator for beta I. Little bi would be its observed value. SE is called a standard error for BI. It's an estimate. You could call it an estimator in the abstract, an estimator for what you could label, say, sigma sub BI. Not the same as sigma in the model. The model had an assumed variance of the errors, the EIs, capital EIs. This is not the square root of that. It's sigma sub BI. It's standard deviation of the sampling distribution of BI. You don't have to put the word sampling in there. Our book doesn't. It just says distribution. But you should know many people do put the word sampling in there. And it's a good reminder of the fact that this is based on a random sample. Standard deviation of the sampling distribution of BI. Some number, and this is an estimator for it. And here is an observed value of that estimator for example, B2, number of bedrooms. Its point estimate is negative 7454.8. Standard error for that is 3521.55. In other words, if we had to, based on these data, if we had to estimate what the sampling distribution of capital B2 would be, I'm saying B2 because bedrooms was the second variable, X2. If I had to estimate what the sampling distribution of B2 looks like, I'd draw a normal curve centered at this number with the standard deviation. It would not be perfect. There would be an estimator, an estimated picture, you might say. But based on these data, that would be my best estimate of what the distribution looks like. And thinking about, roughly speaking, the two, remember the rule of thumb for normal curves, 68, 95, 99.7 rule. For example, about 95% of the data are within 2 standard deviations of the mean. If I draw a normal curve with this mean and this standard deviation, double that standard deviation, it's close to 7,000. What is that telling me? It's telling me in all random samples of size 504 from this population, if I compute the observed value of B2 over and over again, I should roughly expect about 95% of the time to get a coefficient between, say, negative 14,000 something and close to 0. Because this number minus approximately 7,000 is negative 14,000 something, and this number plus approximately 7,000 is close to 0. Zero is sort of on the edge of that kind of thing. So if you think intuitively, are we going to reject a null hypothesis that beta 2 is 0 or not? I'd say we're close to rejection, if not fully rejection. And yeah, looking at the t-stat and the p-value, we would reject at the 5% level. This is just less than 5%. I could report, if I was testing, the null hypothesis that beta 2 is 0 versus an alternative that it's not 0. It's always a two-sided alternative for the p-values in these outputs. Double a one-tailed p-value. If you wanted a one-tailed p-value, you'd want to divide the current p-value by 2. The reported p-value based on these data, well, the t-stat, the observed t-stat is negative 2.1169. Oops, sorry, right here. That's what I just wrote down. And the p-value is approximately 0.0348. Less than 5%, less than, you know, what people typically use as their standard for rejection. Certainly at the 5% level of significance, we've got strong evidence, statistically significant evidence that beta 2 is non-zero. We would reject this null in favor of the alternative. And again, the p-value for a one-tailed test is even smaller. You would definitely reject. Now, again, it's tempting to do the one-tailed test after the fact and say, oh, we got a negative t-stat there. We should do a left-tailed test. That's technically cheating. Not honest. Really, if you're going to do a hypothesis test, you should set up the alternative hypothesis ahead of time before you gather the data. I mean, yes, based on these data, you would reject a left-tailed test with a p-value half of this number. But that's not really how you should approach things. You always should set up your hypotheses in an honest way, do it ahead of time, based on what you think is reality. What's the degrees of freedom here? Is it n minus 1, n minus 2? Got a guess? Anybody do the reading? And tell me the degrees of freedom here. Anybody read ahead? Degrees of freedom for multiple regression is always n minus k plus 1. K is 5 here, right? We've got 5 explanatory variables. K plus 1 is 6, right? That matrix had 6 columns. N minus, in parentheses, K plus 1. Distribute the minus sign through the parentheses. That becomes n minus K minus 1. K is 6 here. So that's actually n minus 7 when you got 5 explanatory variables. Wait, that makes sense? Sorry, K is, I got confused. K is 5. So n minus K minus 1 is 6. N minus 6. When you got 1 explanatory variable, it's n minus 2. When you've got 2 explanatory variables, it's n minus 3. 3 explanatory variables, it's n minus 4. 4, it's n minus 5. 5 explanatory variables, you've got n minus 6 degrees of freedom. This is the DF here. N here is 504, so n minus 6 is 498. 498 degrees of freedom. Hey, look at that. 498 in the Anova part. Yeah, n is 504 here, so n minus 6 is 498. You see the correct degrees of freedom that are used under that DF column in the Anova next to residual. Not total. Don't look at the total. 503 is n minus 1. Don't look at that. Look at the DF that's next to the word residual. Of course, that is a very large degrees of freedom than we typically encounter. And so what that effectively means in practice is the t-stat p-value is not that much different than a p-value you get from a standard normal, z, right? Once your degrees of freedom gets above 100, if we use a normal curve instead of a t distribution, it wouldn't be that much different. That makes sense? I mean, you'd still get this t-stat, but the p-value wouldn't be much different if you used a normal curve. In fact, we could do a little calculation here for comparison. Use equals norm dist. What's the t-stat? Let's go down the row. Norm dist on, yeah, we could do negative 2.1169. 0, 1, for cumulative. So this is going to be a CDF value for standard normal. Area to the left of negative 2.11669 should be close to half of the p-value because this is one-tailed. So if I want the actual p-value close, I should multiply this by 2. So this should be pretty close to 0.035. Yep. That's pretty close to that. So yes, there's 498 degrees of freedom, but so big it doesn't make a ton of difference. Well, how about the confidence interval? And by the way, I don't know why the spreadsheets always do this twice. We only need it once. There it is. Why does XL minor do that twice? I don't know. there's our confidence interval to estimate beta 2. Definitely doesn't include 0. That's more evidence that we reject the null hypothesis that beta 2 equals 0 at the 5% level of significance. And actually, for a two-tailed test, the p-value will be less for a two-tailed test will be less than 0.05 exactly when your 95% confidence interval does not contain 0. Does not contain both positive and negative numbers. You can interpret all the other ones the same kind of way. Testing hypotheses with about, for example, here, beta 0 being 0 or not, based on a certain p-value, and doing confidence interval estimates of those parameters. They're kind of big confidence intervals. We got a good evidence that the, at least for most of these parameters, that they are non-zero, but the confidence intervals are so big that we're not really pinning down the values of those parameters very well. That would greatly affect your application of the model, right? If you actually use the model to make predictions about house prices, the fact that these confidence intervals for the betas are so big should give you pause about how accurate the model is going to be. What else is something practical to think about here? All these p-values are pretty small except for that one. Seems like the zip code is not so helpful. We don't have much evidence that it's not even 0 if we give the assumption that it's 0 the benefit of the doubt. And if beta 5 is 0, or even close to 0, why even bother putting it in the model in the first place? Maybe we should take it out. Would that have any other benefits? Could it possibly, if we take beta 5 out of the model, beta 5 and x5 out of the model, ignore it, could it possibly make these confidence intervals for the other ones smaller, perhaps? I don't know. We'd have to look into it. That'd be nice if that happened. How about this Anova stuff? These are different kinds of degrees of freedom. This is, yeah, n-6. The total DF is n-1. And evidently, there's something labeled a regression DF. What is that? Well, essentially, that's just the number of variables, explanatory variables. Maybe best not to label that with the word, with the symbol DF. The true DF you want to focus on is that one. What are these numbers? SS. This last number, you might want to write this down somehow. They're all very big. This last number is SSYY, our old friend. SSYY. Sum of squares of the y's. SSYY here. We are observing to be this humongous number, 3824076825233. Did I write it down right? $3,824,076,825,233. That's SSYY. That's this summation. and it's 504. I'll go ahead and put a 504 up there. It's this, which you could also write like this. It's actually completely not related to regression at all. If you think about it, just focus on the y values. There's no y hat in there. And remember, actually, yeah, it doesn't come up in the formula for the slope of the regression line. SSYY doesn't. Those other ones. Residual SS. What's that? By the way, this is sometimes also labeled SST, where the T stands for total. Total sum of squares. The other number that I just highlighted there is really SSE. E there stands for error, but error is synonymous with residual. This is the 741429996871. 741,429,996,871. So our old friend SE, sum of squares of residuals. Those things are affected by the regression line. All these numbers are large, but the residual is relatively small compared to the total SSYY. What is that fraction? What's this number divided by that number? It would be approximately the same as 7.4 divided by 38.2. 7.4 divided by 38.2, close to 0.2. What's that? What does that mean intuitively? It means the amount of variation in the y values due to randomness about the model, so to speak, about the regression equation. In simple linear regression, it's about the regression line up and down above the regression line, is relatively small compared to the total amount of variation in the y values overall. And therefore, the regression model overall is doing a pretty good job because there's not much spread. There's not. Again, the relative size of this SS compared to this one is relatively small. It's about 20% of it. In other words, this number, which, by the way, is this number minus this one, this number divided by the total is close to 80%. Is that a measure of the strength of the regression? This number's close to 80%. R squared. What is that? Is that the squared correlation? Not in the usual sense, it's not. But it is labeled R squared. And it's still called the coefficient of determination, though we often put the word multiple in there, coefficient of multiple determination. It's about 80%, relatively close to 1. This is a pretty good model overall when that number is relatively close to 1. You might wonder what this multiple R is. I'm not going to get into that today. Or the adjusted R squared. I'm not going to get into that today. The fact that this one's relatively close to 1, it's not super close, but it's pretty close, means this model overall is doing a pretty good job. The standard error, as before, is labeled S, and it is an estimate for sigma, where sigma squared is the variance in the model. And yeah, there are 504 observations. These two numbers down here do have to add to this. And yeah, this R squared here, this 0.806, should be this one divided by this one. Let's see if that happens. This divided by this. Yep, 0.806. These numbers that you see here are labeled MS. That stands for mean square. This number right here is this one divided by this one, dividing by the degrees of freedom. This one is this one divided by that one. And then this F statistic is this number divided by this number. Try it. It's very large, 414, very large observed value of some F statistic, and the corresponding p-value is essentially 0. More confirmation that overall the model is doing a very good job. There's a more precise way to say that, but I'm not going to take the time to do that today. You'll find it in the reading. Starting, I think, in section 12.5, if I remember correctly. So what we've just done is essentially summarize briefly some things in 12.3, but also gotten spreadsheet output for what you would find from this formula. Confidence bounds for beta I, the ith model parameter in the general linear model. Beta I hat is essentially little bi. There's your t value. There's S. That's going to be the regression standard error right there. That's the thing labeled S. What's this? Square root of CII. That's what we have left to explain in our last 10 minutes today. CII, if you look on the previous page, is the element on the main diagonal of row I plus 1 in this matrix. If we're going to use the formula in the book, we've got to calculate that matrix. Spreadsheet, unless there's some package I don't know about, can't do that. Maybe there's some package I don't know about that does it. We got to compute X transpose times X inverse and look at its elements on the main diagonal if we hope to use the formula that I just showed you. Spreadsheet seemingly can't do it. How about Mathematica? And at this point, this is where we'd use R next time. So I will email this Mathematica file to you. Somebody could send me a quick email to remind me so I don't forget. But I've got my spreadsheet data and I can access it by importing it like I showed you before. And if you click on this thing here, you can click down to a file browser. Probably gonna need to look up on my screen here now. Square bracket, file browser to browse for your spreadsheet. And what did I call it? Home and price data. Okay, that'll give you the correct path. There we go. There's your variable names, including your observation number, price, square footage, bedrooms, bath, garage, and zip. Unfortunately, the raw data is not in the most ideal form. To get the data itself with labels, let me call it this, data with labels, I need to do this, raw data 1. That essentially gets rid of the outer set of curly braces, and this is easier to work with. And I included the labels in there. If I want just the data themselves, I can use a built-in Mathematica function called drop to get rid of the labels, obs, price, square footage, etc. I believe it's drop that will do it. You can look it up to make sure. Look up drop. Yeah, drop will take a list and drop the first n elements where you put the number n there. So if I do drop data with labels, comma 1, that'll drop the labels. Now you only see numbers. And there should be 504 data points in there. If I do length data, there should be 504. That's including all the variables. Actually, I think I'd like to get rid of the observation numbers as well. Let's do a 2 here instead. Did that do it? Wait a minute. Am I using drop correctly? First n elements dropped. That should have worked. Oh no, okay. I'm thinking about it wrong. Okay, so this is the data. Organized as a 504 by 1, 2, 3, 4, 5, 6, 7 column matrix. I'd like to get rid of that first column, which is just the observation number. Oh, I shouldn't have left this for myself just 10 minutes for this. Let's see. Let's see what happens if I transpose the data. Transposed data, which essentially transposes this thing as a matrix. Well, and let's not look at the matrix form. Let's look at it in its list form. Okay, now what this has done is this has put all the observation numbers in a big list first, then all the prices, then all the square footages, etc. And now I think if I let's call it working data, if I get rid of those if I get rid of that first list with drop again, then it would be just the numbers. Now that's just the prices and the square footages and stuff. Yeah, now, okay, this is good. So I can now do price is working data 1. Those are just the prices. I should call it prices. I could do square footage as working data 2. Those are just the square footages. I could do bed as working data 3. Those are just the number of bedrooms. Bath as working data 4. Number of bathrooms, including half baths. garage as working data 5, many of these were zeros, and zip as working data 6. Okay, is this the best thing to do? What I'm trying to work toward is my design matrix X. Let's see what happens if I do this. Sometimes you just kind of got to experiment. Don't put the prices in there. Put square foot. Put a bunch of ones, right? For like the first column is all ones. I'm going to try it this way: 1, comma, prices, and then you need an I in there. I is going to go from 1 to 504. Square foot, bed, bath, garage, and zip. I goes from 1 to 504. Is this in the right format? Let's look at this in matrix form. Yeah, that looks like the design matrix that we need. That looks like capital X, right? One's in the first column, the values of the first variable, square footage in the second, the values of, no, these are prices. Wait, I didn't want the prices in there, did I? I don't want the prices in there, sorry. It's a 504 by 6 matrix. There we go, I got rid of the prices. The Y vector, I could just do the prices. It is being represented as a column vector, that's good. And as far as doing what I was showing you in the book, we need to compute the inverse of X transpose times X. Let's see if Mathematica can handle it. Matrix form, inverse transpose X times X. If Mathematica can handle this, it should be a 6 by 6 matrix. There we go. And the CIs are supposed to be these numbers on the main diagonal. CII is in the main diagonal on row I plus 1. So this would be like C11 would be this number, very small. C22 would be this number. C33 would be this number. C44 would be this number, etc. Wait, did that work? That'd be C55. Yeah, there's 5 variables. I guess that works. It's a 6 by 6 matrix, but we're essentially ignoring the first column and first row, I guess. And then you could use those numbers in conjunction to confirm this formula. We're out of time. I will take some time after class today to see if that really worked and match the spreadsheet. And that'll help me decide whether to assign something like this or not. Okay, you don't have to completely understand what we did in Mathematica, just mimic it. I'll share the file.